What lies inside a black hole is one of the biggest mysteries of physics. But in recent years, a new paradigm has arisen from string theory, suggesting that we should replace our traditional notions of black holes with a new object, a fuzzball. In this film, we'll explore this concept with the father of fuzzballs, Samir Mathur, his colleague Nick Warner, a former student of Stephen Hawking, and astrophysicist Niayesh Afshordi, who has developed an idea that may enable us to peer into a black hole and see what's really lying inside. Our journey begins, like much in black hole physics, with Stephen Hawking's work of the 1970s and 80s.
At the time, Stephen's voice, he could speak, but it wasn't comprehensible to people who didn't know him well. And so I and his other students and postdocs and colleagues would translate his voice into, well, give him a voice that could be understood and heard by others. What Stephen means by this is that space-time is some compact four-dimensional manifold. When you translate Stephen, the signal-to-noise ratio is about 1. And so you really have to focus and concentrate on what he's saying. And so in doing that, you have to devote almost all your brain power to, or at least when you first do it, devote your brain power to the translation process. And so the words that I'm actually saying, I cannot retain, and certainly not the physical concepts. So I sometimes joke that I'm the stupidest person in the room because I literally don't know what I'm talking about.
So what Hawking found was that if you take the theory of general relativity, which everybody knows and loves, it's been there for a long time, was discovered by Albert Einstein. And then on the other hand, you take quantum mechanics, which is also a theory we all know and love, developed over several decades. And then you try to put them together, you'll actually get an inconsistency.
This inconsistency arises when we consider the collapse of a sufficiently massive star.
Just because it's a runaway collapse, the denser it gets, the more strongly it attracts, it keeps shrinking and shrinking, all goes to a point. And when something becomes that dense, then what Hawking found was that the entire empty region outside, we call it the vacuum, it actually becomes unstable. It becomes unstable in the sense that it starts spitting out particles. So particles keep getting spit out from the vacuum, and the black hole starts losing its mass, and in the end the black hole will go away. So up to here it looks fine. If you're going to, let's say, burn a piece of coal, you know the coal will disappear, it will become some radiation, and there's nothing wrong with that. But there's something wrong this time, because when you burn a piece of coal, what comes out are the pieces of the coal. So the information in the coal shows up in the radiation. And by information we mean if I took a different piece of coal or a piece of a different material, the radiation I collect will be different. But now look at the black hole. The radiation this time came out from the vacuum. It was pulled out of the vacuum. And so it doesn't matter how you made the black hole, doesn't matter what went into the black hole, what comes out is going to be the same.
If you make black holes out of different things like hydrogen or books or conservative politicians, then they all look exactly the same. And if you make them of the same mass, then they will radiate in Hawking radiation in exactly the same way. And so the end result of that is the final state, no matter how you make the black hole, the Hawking radiation is absolutely identical. Now in quantum mechanics, there's this principle called unitarity, and it simply says that if you make a final state, you should be able, from that final state, to be able to reconstruct the initial state of what the black hole was made from. But the process of Hawking radiation, forming the black hole and the Hawking radiation, washes all the information out of the constituents, so the final state cannot be used to reconstruct the initial state. And that Hawking process is thus a direct violation of unitarity in quantum mechanics.
So it's such a big deal because the whole philosophy of physics is based on the fact there will be an equation which will tell you how to go from here to there. And now there cannot be an equation. So that's why the breakdown is really very serious. It's really attacking the whole foundations of how we thought we should do physics.
So given that there's this foundational conflict between quantum mechanics and general relativity theory, every theorist who thinks about these problems has to decide first which of those they're going to throw under the bus. Well, Stephen was raised in general relativity theory and made amazing foundational contributions to the subject. And so it's pretty clear that he was going to want to revise quantum mechanics. And that's in fact how he first approached the problem, the information problem. Indeed, when I was one of his student, I went to Oxford with him and I gave one of his seminars on exactly revising quantum mechanics. It was absolutely terrifying.
String theory holds on to the basic tenets of quantum mechanics, positing that reality isn't made from point particles, but instead extended objects like strings or membranes. But why should this make a difference to black holes?
You might think, and people did think, that if you put many strings and brains together, they would again attract themselves under the force of gravity and would all shrink to a point, and it seemed you'd be back in the same troubles as you would before. But what happened was, when we actually tried to put these strings and brains together to make a black hole, we got a surprise. And the surprise was that instead of shrinking under the force of gravity all the way down to a central point, the way classical physics had predicted and the way Hawking had assumed, this collection of strings and brains refuses to shrink. Now, if they don't get pulled in and they actually make a big object, it's more like a star or a planet. Well, this is like a normal body. This normal body doesn't have all the mass in the center and a vacuum outside. In this case, you're not going to get some radiation being pulled out of the vacuum. This object would radiate from its surface like a normal piece of coal, and then there is no paradox.
This new object is called a fuzzball, and it differs from a black hole as its gravity isn't strong enough to pull particles out of the vacuum. But why? The answer comes from the most famous equation in physics, E = mc². Particle colliders like the LHC use this to convert energy into matter, but for gravity, things are different.
If you go to a waterfall or to a hydroelectric power station, gravity pulls things down, and you pull things down, the potential energy of water is lost. It turns into energy of motion, what we call kinetic energy, and that's what we extract to power our homes. So when things fall under gravity, they release energy, potential energy. And so that's what's happening inside a black hole. The energy of potential energy of gravity, the same energy which happens when water falls down a waterfall, now the water is falling so deep that you can fall so deep that you can actually have enough energy to actually create particles using E = mc², and that's where these particles are coming from. Well, to do this, you've got to be able to come close enough to a dense source of mass so that you can actually get enough gravitational potential energy to create a particle through E = mc². But if the object is fluffed up and has a size like the Earth, or the Sun, or any other star or planet, the gravity in there never becomes strong enough for this to happen. And that's what happened with the fuzzball, because the whole thing fluffed up into what you might call a string star. Okay? There just is none of this strange Hawking way of producing particles, and it's now just like a piece of coal or a planet, and there's no puzzle.
There isn't an information problem with white dwarfs, and there isn't an information problem with neutron stars. The problem is the horizon. A black hole has a horizon, and that's what creates the Hawking radiation. The whole point about fuzzballs is there isn't a horizon. It's another state of matter that can hold up a huge amount of mass and stop a black hole horizon forming. There is simply not an information problem with fuzzballs.
The whole key to solving the black hole puzzle was that in string theory, the objects are not point-like particles which can race around the way we always thought in particle physics. They are like strings and brains, which are what we call extended objects. They have a size. So the reason the black hole puzzle was solved is that anytime you try to make a black hole out of point-like particles, they all rush to the middle the way everybody thought. But if you put energy in a string, it can go into two places. You can make the string move faster, just like a particle, but you can also put it into stretching the string. And there are many more ways to stretch a string as compared to just moving it. And so just on the laws, based on the law of thermodynamics, the energy actually goes preferentially towards stretching the string. The guy becomes so big that it becomes this fuzzball, and that's how the puzzle was solved.
To resolve the black hole information problem, you have to find structures that can store the information and then recycle them back into the universe. And Samir started in a very small but simple example where he used structures in string theory and showed that they could store information and ultimately then recycle them back into Hawking radiation with the information encoded in that radiation. The problem with Samir's calculation is that it was very idealized and it was extremely simple. It was compelling and really interesting and suggestive, and it was great science, but it just wasn't strong enough to convince, I think, a lot of people. I got involved in this problem because Joseph Benner and I really wanted to try and get to the bottom of whether we could make something a bit more realistic, something which actually was like a black hole with a huge horizon, but actually didn't have the horizon. And so we started looking at the equations, and I was pretty convinced it was not going to work. I was actually got into the problem with the intent of showing that it was actually unsolvable with the mathematical techniques we have to hand. And I was certain that was what was going to happen. But when Joseph and I got into down to the bottom of these equations, we found that the actual equations that we needed to solve were linear, and therefore we could solve the hell out of this system.
With solvable equations, it became possible to further probe the fuzzball and see if it reproduces the famous prediction of Hawking radiation.
You still emit radiation. And very interestingly, for reasons we now understand, it also comes out at the same rate as the one that Hawking had found, but doesn't come out of the same process. So Hawking's radiation came out of particles being pulled out of the vacuum in the way we just described. But now the radiation comes out the way it would come out from any other body. So if you have a hot piece of coal, what is happening is a little piece of coal, an atom just breaks off and flies towards us, and the coal slowly evaporates. So the puzzle is gone because now this object radiates like a normal body, and when a normal body radiates, what's coming out are pieces of that body, and so all the information is preserved. The reason Hawking had a puzzle was that all the matter went to the center in the central dot, and the energy was radiated away from somewhere else out of the vacuum. And now that's not happening anymore. So the real lesson here is that somehow the string theory is clever enough to never allow you to make a region where gravity is strong enough to have this magical Hawking's instability of the vacuum.
Normally, we think that if we cross the event horizon of a black hole, we're trapped. But as a fuzzball is more like a star, could we escape its grasp?
The reason you got trapped inside the black hole is that from there, if you wanted to come out, you'd have to fly faster than the speed of light, which we are assuming we can't do. If you go into the sun, you have troubles, but they are different troubles. They have nothing to do with the speed of light. You'll get broken up into pieces because you'll collide with all the hot atoms in the sun, and you'll become part of the gas of the sun. But ultimately, all the gas in the sun, it does leak out. So you will get damaged and sort of destroyed, just like you would get destroyed into a star. But it's not a conceptual problem. It's as bad as, falling into anything. It's a mess when we pull you out, but you can be pulled out.
Another key difference between fuzzballs and black holes is related to quantum tunneling, where particles travel through apparently solid barriers. But what are the chances that this could happen for a macroscopic object?
As a macroscopic object, the probability of me tunneling anywhere is insanely small. But the really important thing to appreciate about a black hole, which makes all the difference, is the fact that there's an insane number of states that a black hole can have. And there's a rule in physics called the Fermi Golden Rule, and it says you take the probability of a quantum tunneling event, but you have to multiply it by all the places you could go. So normally this is not an issue, because if I'm sitting here and I'm thinking about tunneling into London or to Paris or Istanbul, there's only a few places on Earth I can go. But suppose I had a black hole nearby, like in the kitchen. If there's a black hole in my kitchen, there's an insane number of states in that black hole into which I could tunnel. And I take that huge number of states, the number of those states, and multiply by that small probability, and the number and the probability becomes of order 1. And as a result, a black hole we now understand to be an intrinsically quantum object at its horizon scale. And so it makes all the difference to the physics. The experience of actually falling into a black hole can thus be described in two ways. In the traditional way in general relativity theory, as you fall in, the tidal forces get large, they start pulling you apart and spaghettifying you as you go towards the singularity. But in the quantum description of a black hole, now we realize that the fuzzball on the black hole is intrinsically quantum. What happens is this incredible number of states and excitations of the black hole start literally knocking pieces off you. And it's called quantum decoherence. Your state sort of mingles into all those other states of the black hole, and you sort of dissolve into the fuzz.
Solving the information paradox is all well and good, but we need observations to really confirm the paradigm. And for that, something would have to come out of the fuzzball.
It's very hard to actually get something to come out of the fuzzball because the fuzzball is like a black hole from the outside. When this fuzzball does radiate something trying to send it outside, the gravity of this object most of the time just pulls it and makes it fall right back in. So very little stuff actually comes from the surface of this fuzzball out to us. So we did a calculation of that, and we found that only 1 part in 10 to the power 77 of the stuff being radiated from the surface actually makes it out. But here there was an interesting result of Afshordi and his collaborators here at the Perimeter Institute, who found that if you take low energy electromagnetic waves and send them onto something like a fuzzball, they will actually scatter off, while if you set them onto a normal black hole, they will get absorbed.
If you send a signal into a black hole with a horizon, nothing will come back.
If you replace horizon with something different, then you're going to hear back something. Basically, the same way that if you shout into a well, if it's a bottomless well, you're never going to hear any echoes. But if there's a bottom, at some point, you're going to hear back echoes of what you shouted into the well. So that was the main idea. And then it occurred to me that there are no bottomless wells in the universe, at least not on Earth. And probably, if anything has finite amount of information included in it, then it cannot be bottomless. So maybe there must be echoes, and maybe we should go and look for them.
Such an echo could enable us to peer inside a black hole.
Basically, the same way that molecules or atoms give us a microscopic picture of air or water. So if you have a microscope and we could really see into details of water or air, we could see these molecules and atoms. If we had a good way of probing the microscopic structure of black holes, instead of seeing what Event Horizon Telescope sees, which is what the back of my head, you would actually see this more detailed microscopic structure that could be one or many of these fuzzball solutions. Well, microscope, the way that it sees things, that you should shine a light at something, or shine, like for an electron microscope, you shine electrons at things, and the electrons that are reflected back is what's detected. So for gravity, we have gravitational waves that can be emitted at these fuzzballs, and the reflection of those gravitational waves, if we have very good detectors, can be seen.
But if an echo were detected, what could we learn?
Just seeing an echo who just says that there's a bottom of some type. And then the next step is to see, and this would be some sort of a joint collaboration between theorists and maybe people who do computations and maybe experimentalists, to actually infer whether it's a signature of fuzzball or some other proposal for quantum gravity. And it turns out that it's hard to actually go from these theoretical solutions to actual observations. So in principle, if we have a detailed signal, we should be able to backtrack and say what type of a space-time this came out of. In practice, I think it's a more complicated exercise, and hopefully that's the bridge that we cross when we get to it.
It's extremely important to try and figure out an observational signature that will distinguish a fuzzball from a traditional general relativistic black hole. And so we've had a very lively discussion with various and differing views on what the sort of signature differences might be and how we might see and distinguish between fuzzballs and black holes. Some of the discussion of this has been centered around what happens when you ping the object with an incoming probe. Does it return, and how does it return? And so, in particular, this is sometimes called echoes. Now, a lot of the early calculations here have indicated that the echo, there will be an echo, the probe will come back, much like when you send a sonar wave and it hits the bottom of an ocean floor, you get a ping back. But more recent calculations I did with Emil Martinek suggest something a lot more subtle and difficult, because what happens is, as the ping goes in, it actually has to be built out of strings, and those strings then merge into the fuzzball and get absorbed. It's a bit like when you have a sonar wave, rather than bouncing off the hard floor of an ocean, imagine there's 1,000 feet of sponges, and the ping goes in and then just dissolves or disappears into the absorptive surface. So the issue with the echo is then, what is it going to be and can we see it? And the calculations we did suggested that if there's an echo, it's going to be a lot softer and a lot more subtle.
But echoes are not the only way to probe the interior of a black hole.
Another interesting idea is things that happen far away from the black holes. For example, again, this image you see behind me is the first image of the space-time of a black hole given by or taken by Event Horizon Telescope. And it does probe the structure of the space-time around a presumably rotating black hole. And you may think that if you have anything other than the standard solutions to Einstein theory of gravity, you may see subtle differences in these images. So that doesn't necessarily require you sending signal all the way to the horizon or back, but it just tells you that even far away, the solutions may be slightly different. The same way that, for example, the gravitational field of Earth is a little bit different because Earth has some shape which is not exactly spherical.
Fuzzballs have been associated with a new type of energy called VECRO energy.
In quantum mechanics, everything jitters around, so the particles come and go. We call them virtual particles. So the V stands for virtual. Next letter is E. It's extended. The whole key to solving the black hole puzzle was that in string theory, the objects are not point-like particles which can race around the way we always thought in particle physics. They are like strings and brains, which are what we call extended objects. They have a size. So the reason the black hole puzzle was solved is that anytime you try to make a black hole out of point-like particles, they all rush to the middle the way everybody thought. But if you put energy in a string, it can go into two places. You can make the string move faster, just like a particle, but you can also put it into stretching the string. And there are many more ways to stretch a string as compared to just moving it. And so just on the laws, based on the law of thermodynamics, the energy actually goes preferentially towards stretching the string. The guy becomes so big that it becomes this fuzzball, and that's how the puzzle was solved. So now the extended nature of objects in string theory are therefore completely crucial, and so VECRO stands for virtual extended. The C and the R actually are also important. They stand for compression resistant. Once you make this kind of object, this stringy fuzzball, it doesn't want to compress, costs you energy. Just like if you try to compress a star, it costs you energy. It doesn't want to stretch either, it costs you energy. And the O is just object. So virtual extended compression resistant objects.
Most cosmologists think the early universe underwent a rapid period of accelerated expansion called inflation. And a second, more gentle period of accelerated expansion is still happening today and associated with what is called dark energy. However, two independent measurements of the expansion rate do not agree, and it's possible that this Hubble tension can be explained by a third period of accelerated expansion known as early dark energy. But some have claimed that these solutions require delicate fine-tuning. Can VECRO energy resolve this?
If you try to put in the energy of inflation at how much energy there should be to get inflation, you have to put that value in by hand. And also for the dark energy today, it's a very small value. And one of the puzzles is, well, we can put it in by hand, but such a small value, it looks really like we are fine-tuning something. But in the way we are thinking now through fuzzballs, both these things are completely natural. So what happens is every time the universe is expanding and it changes the rate at which it is expanding, this kind of VECRO energy gets induced, but it gets induced with a value which is equal to the energy density, roughly speaking, at that particular era in our expansion. When you have this change, you will induce this extra energy, but with an energy density, which is the energy density of the universe at that epoch. So this kind of energy is getting induced every time there's a change in something else, the rate of the nature of the expansion rate. And so it's not a fixed number which you have to put in by hand, and then you could ask, why should the theory have this number or this number? It's something which is just happening at different epochs because the expansion history of the universe is so complicated. And it's somehow coming in automatically at the right times and places and the right scales to account for the three puzzles we have. What triggers inflation? How do we get early dark energy to account for these Hubble constant puzzles we are facing? And what could account for the dark energy today?
The ultimate mystery is, of course, how did the universe get here? If fuzzballs can resolve a black hole singularity, can they do the same for the Big Bang?
everybody agrees that singularities are a problem. And in black holes, we have this idea that the fuzzballs remove the singularity in the horizon. But there's another singularity, the cosmological singularity, the Big Bang. And everybody also agrees that that's not an adequate description of that event. So we believe that the fuzzball description, or some version of it, will give us a much better description of the state of matter in the very, very early universe. Samir's been working on this with his VECRO hypothesis, but it's extremely hard to do, simply because the early universe is evolving so fast, the problems are just too damn hard, and that's why I work in black holes. But Samir, I think, ideas are very interesting, but they're very much in their infancy, and they're basically the state of the art there is like it was with fuzzballs about 25 years ago.
As you go towards the Big Bang, you are going into a certain limit where things are becoming very hot and very dense. Normally, when you go to some kind of a limit in a theory, things simplify. For example, even if you take something as complicated as the strong interactions, when you go to very high energies, it actually becomes what's called a quark-gluon plasma. It's a theory of free particles. So you could ask the same question of string theory. Now here we have a well-defined theory. If you go to the limit where you have very, very high energy densities going all the way towards infinity, let us say, which is what we expect towards the Big Bang, in that limit, can you tell me how this theory is supposed to behave? For example, there's supposed to be what we call the equation of state in a theory. How much pressure do you get for how much density? There seems to be a unique equation that is actually arising as an answer to this question. That equation has been discovered several times in the past. It comes from what is called the black hole gas. So if you imagine that when you get to very dense situations, what you have is densely packed black holes. It actually gives you a state which has the maximal possible disorder for that much energy. And it has a very well-defined what we call equation of state. The pressure is exactly equal to the density. And what that means is the speed of sound, which is normally much smaller than the speed of light, in that limit becomes equal to the speed of light. It's just a very beautiful answer, and what is surprising to me is that many different roads have all led to the same answer. But if you ask which kind of equation of state can you get in string theory, which actually preserves all the symmetries of string theory, these symmetries called dualities, there's a unique answer. And that answer is this particular black hole gas equation of state. So I have begun to think that any answer of what happens at the Big Bang must be somehow connected to our landing up in that equation of state and then trying to understand the Big Bang in terms of this densely packed gas of black holes. So if we have understood what's happening inside a black hole, it's the same stuff which should automatically become what describing the very early universe. In black holes, we didn't have a singularity. So in some way, there shouldn't be a singularity at the Big Bang. Its nature is less clear to me. It's something I very much would like to understand.